Hey guys, today we're going to go ahead and talk a little more about gas laws and stoichiometry. In the previous video, we did gas laws just using masses of gases and going through predicting products and reactants, doing all that. Now we're going to go ahead and do another way that you can measure gases, as they are typically very, very difficult to actually measure other physical qualities of. The other way you can do it is we can measure through liters or volume. And to do that, though, we need to be able to convert that again into quantities so we can use chemical reactions, stoichiometry to get there. So we need to figure out what's this thing called STP means and why do we use it. So to start out with, we're just going to go ahead and do this quick problem to justify and find what this STP, or standard temperature and pressure. Sure. And wow, it was a terrible and pressure. Alright, so if I have how many liters of space, we're going to see we have a number of moles of 1 mole of a gas. 0 moles. We have a temperature of 0.0 degrees Celsius. As always, I'm just going to go ahead and convert it into Kelvin right away for myself. 3.15 equals 273.15 degrees Kelvin. And then we have a pressure of 1.00 atm. Of course, I know that with these three things in R, I of course can use the ideal gas law to find a volume. So we're going to go run through that. You guys know how to do this. We're going to rearrange real quick, get what we're solving for, which is the volume. That's the problem I'm asking for. So divide by P, P and P cross out. We have V equals moles times R times T divided by the pressure. And that ends up being, as we substitute in, 1.00 mole times R, 0.6 liters atm, divided by moles Kelvin, times temperature of 273.15 degrees Kelvin, divided by P, pressure of 1.00 atm. And then we're going to go ahead and plug on 1 times 0.08206 times 273.15, wow, and divided by 1, and that of course ends up being 22.4 liters. So we say that if a gas is at these things, it takes up 22.4 liters, and this is where we get this STP, or standard temperature and pressure, from. We say standard temperature, we use 0 degrees for standard, and we use 1 atm, or 1 atmosphere. At STP, we see that if we have 1 mole of gas, it takes up 22.4 liters. So we just use this number of STP equals 22.4 liters per every 1 mole. So if I had 1 mole of any gas, it's going to take up, or occupy, it's just going to occupy, because of course there's lots of empty space between gases, it's going to occupy 1 mole. So 22.4 liters of gas is the same thing as saying 1 mole gas if you have a standard temperature and pressure, or they're at 0 degrees and 1 atm. So we're going to use that to solve a couple problems. First, we're going to see, hey, does this STP thing work? I'm going to go ahead and throw it up with my constant. 22.4 liters per mole. And we'll go on to the next. See if how well this will work out. Okay. So for our next problem, we're going to go ahead and say, hey, Sean has a 1.59 liter container filled with oxygen at 0 degrees and 1 atm. How many moles of oxygen are in the container? Now, there's a couple of different ways that we could solve this, of course. The first way, we could say, hey, I have a volume of 1.59 liters. I see a temperature of 0 degrees Celsius, or 273.15 degrees Kelvin, and a pressure of 1.00 atm. Couple ways we can do. First, I could say, hey, look at this. This is STP. So I could just use dimensional analysis to figure out what the moles of gas, because I know that if I have, for every 22.4 liters, I have 1 mole. So I can just go ahead and use dimensional analysis real quick to see that. So starting with 1.559 liters of O2, and if I divide that by 1, of course, put it as a fraction, and I want to go ahead and convert it into moles, find out what that means, I'm going to do and say that for every 1 mole, I have 22.4 liters. Liters and liters cancel out. I'm going to have an answer in moles of O2, and I see that the number is 0.079821, 1.59 divided by 24, or 0.0710 moles of O2. Okay, so let's see if that works if we just use the ideal gas law like we've been doing. So we start out with PV equals nRT. We need to solve for moles, of course, is what we're looking for. So we need to get it by itself, divide by RT to cancel those out. Cancel, cancel. We get N equals PV divided by RT. We start plugging in. We see pressure of 1.00 atm times a volume of 1.59 liters divided by R, which is 0.08206 liters atm divided by moles Kelvin, divided by temperature of 273.15 degrees Kelvin. Plug in 1 times 1.59 divided by 0.08206 divided by 273.15, and I end up with, cross out, oh, mole stays. Liters and liters, Kelvin, Kelvin. We get a number of 0.0710 moles. So it ends up being the same thing, whether we just convert it straight up or not. Now, second part of the question, if the cylinder was filled with nitrogen instead, how many moles of nitrogen filled out? So if I just started with nitrogen again, you can see if I start with 1.59 liters of N2 instead, I would have 1 mole. I want how many moles I get, so if I have 1 mole, it would be 22.4 liters, and I end up getting that 1.59 liters of N2. Every 23.4 liters of N2 is 1 mole of N2, liters, and I get 0.0710 moles of N2. So this number works for any kind of gas at standard temperature and pressure. So if any gas is at 0 degrees Celsius and 1 atm, you can use this number of 22.4 liters per mole to get into the quantities, because of course stoichiometry, if we use chemical reactions, we got to get a physical quality like grams or liters or anything else we can measure into a number so we can bring it across the chemical equation and solve to predict a product or reactant, which we're going to do in the next problem. Okay, so our next problem says if we have solid potassium chloride decomposes into potassium chloride and oxygen. If you start with 25.6 grams of potassium chloride, how many liters of oxygen are produced at STP? So what do we know? We know that we have 25.6 grams of potassium chlorate, ClO3, and I want to know how many, the volume, or how many liters of oxygen we need. We see that a chemical reaction is taking place, so let's go ahead and set up a balanced chemical equation for this reaction. Solid potassium chlorate, so KClO3, solid, decomposes into potassium chloride, KCl, solid, and oxygen gas. Let me go ahead and balance this. Sure, we need 2 of those and 3 of those. That means we need 2 of those. So of course this chemical equation says for every 2 potassium chlorates, I will get out 2 potassium chlorides and 3 oxygen gases as it decomposes. And I can use this, go ahead and use stoichiometry to solve this real quick. So I set up with what I have. I have 25.6 grams of potassium chlorate over 1, right, as a fraction. And then I need to go from grams into moles because, of course, this means a number thing. So we always get our measurable physical quantities into numbers before we go across the chemical equation to predict something. So I need the molar mass of this. So molar mass of KClO3. And we see that that is, of course, is 1 times molar mass of K plus 1 times molar mass of chlorine plus 3 times the molar mass of oxygen, which is 39.1010 plus 35.45 plus 3 times 16.00, and I get a number of 122.55 grams per mole. As I'm coming from here, I have 25.6 grams of potassium chloride. I want to know how many moles. I know that for every 122.55 grams of potassium chlorate, I get 1 mole of potassium chlorate. Okay, so now how moles of potassium chloride. Now that I have this, I know that for every 2 moles of potassium chloride that decompose, I'm going to get 3 moles of oxygen gas out. So I'm going to use that. Go ahead and say I put in 2 moles of potassium chloride, and I get out 3 moles of O2. Now I have moles of oxygen gas. Now I can go straight to liters, continue to use dimensional analysis, and go to liters of oxygen. Because I know for every, if it's a standard room temperature and pressure, I have 22.4 liters for every 1 mole. If I stopped here, I would have moles of O2, so I can just keep going and say for every 1 mole, I have 22.4 liters. And that can be for any gas. I'll say in this case, of course, it's O2. I like to carry my units there, and then I'll go ahead and cancel units. Grams to grams cancels, moles to moles of that, moles of O2, moles of O2. I have liters of O2, and I end up getting, we got 25.6 divided by 122.55 times 3 divided by 2 times 22.4. We get out 7.0188473, or sig figs, we get 7.02 liters of O2. So we can go ahead and solve out for that using STP. All right, we're going to do one more problem using STP to predict this stuff. Go ahead and read through it as I erase. Set up your next problem. How much I use my notes there? I got math on it. Okay, so on the next problem, we have silicon dioxide reacts with carbon to produce silicon carbide and carbon monoxide. I can already see I'm going to be needing to predict a product or reactant from this. If you need to make 23.5 liters of carbon monoxide, how many grams of silicon dioxide do I need to buy? So clearly it looks like we're buying a reactant and we already have the number of product we need. So I know that I'll have to make a volume of 23.5 liters of CO, or carbon monoxide. And I need to know how many grams of silicon dioxide, which is a solid at room temperature, do I need to buy in order to put that in. So go ahead and use balanced equation to start setting this up. I have silicon dioxide, SiO2, which is a solid. It reacts with carbon, solid, and it makes silicon carbide, which is solid, and carbon monoxide gas, which is what we're looking for. Go ahead and balance it. I always leave my lines to give myself space. Let's see here. I have 2 oxygens. I need 2 oxygens on this side. I have 1, 2, 3 carbons, so I need 3 carbons, and I have 1 silicon, 1 silicon. We're good. Now we go ahead and start plugging. I start out with a measurable physical quantity, 23.5 liters. Measurable, but gases, of course, are difficult to do so with, of carbon monoxide. We're using STP. Since it is at STP, we're going to assume we're going to go ahead and use this formula to get into moles. So I use numbers to go across, and we go ahead and see if for every 1 mole of any gas, in this case carbon monoxide, at STP, I have 22.4 liters. So now we have moles of carbon monoxide we need to make. Now we need to revert back to the reactant. So, of course, for every one of these, one silicon dioxide that I use up, I get 2 carbon monoxides. So 2 moles of CO for every 1 mole SiO2. And now, of course, I need to go from moles back to what the problem's asked for, is grams. To do that, I need a molar mass. Molar mass of, what we're going for is silicon dioxide. And that would be 1 times the molar mass of silicone plus 2 times the molar mass of oxygen, which equals, of course, where's my notes yet? 28.08 plus 2 times 16.00, and that is 60.08 grams per mole. So if I want for every mole of silicon dioxide, oops, that's not where that goes, of course, because that will not cancel out. For every mole of silicon dioxide, I get 60.08 grams of silicon dioxide. Go ahead and solve out and make sure I have my units like I want them. Liters of carbon monoxide, liters of carbon monoxide, moles of carbon monoxide, moles of carbon monoxide, moles, moles, and I have grams of silicon dioxide, of course, which is what I want. We do 23.5 divided by 22.4 divided by 2 times 60, and we get 31.51578, or in sig figs, we get 31.5 grams of silicon dioxide, which we would need to buy in order to produce this much gas. All right, well, thanks for watching. Hope we understand using these gas laws a little more, and hopefully in the future we'll be able to combine using both the ideal gas law and STP, depending on what gas we need or we can find, as we continue stoichiometry. Thanks for watching.